All right, so we're going to finish up with that sample midterm, and then we'll dive right into chapter 9. So let me go get the sample midterm that is open. And we'll carry on. All right, let's see, where are we? So I believe we left off with problem 8, which is all about probability theory. So from going forward, the rest of these questions should be about either probability theory or else they will be about binomial distribution, the normal distribution, or the Poisson distribution. All right, so let me get this open. And the solutions we've done so far are posted. So today we'll add, I guess we'll call it part 3, and that will be the rest of it. So they're all broken up into pieces, partially because of the size issues. I did mention yesterday, I think that one of the drawbacks to using the tablet is that it just sucks up an awful lot of memory. Oh, wait a minute, I grabbed the wrong one, sorry. Yeah, and so what can happen is if I've got too much of it on one document, it can cause serious problems, and it's actually possible to lose what I've done if I'm not careful. So there we go. All right, let me save this real fast. So this way, by breaking it up into smaller pieces, that at least reduces the risk of that problem. Okay, hold on 1 second. So today's the 5th, but this is now part 3. And the last one we did was oh, that's right. So we've already done even the probability theory. All that's left is the discussion about random variables, the binomial distribution, the normal, and the Poisson. All right, so we'll start right here. So the following table gives the probability distribution for random variable x. Now, this is not binomial, it is not Poisson, it is not normal. It is a probability distribution, but it doesn't have a particular name of its own. Most distributions don't actually have a name. There's just a handful that are so useful and so important in practice that we do give them their own special name, but most of them are just, whatever we're using at the moment. This is one of those cases. This is some experiment that's taking place where x can only equal 100, 300, or 500, and those are the corresponding probabilities. Now, we know that it's, and that's one of the questions, we know that x is discrete because it can only attain 3 different values. And since 3 is a finite number, that means that x is considered to be discrete. But first things first, is this a valid probability distribution? Why or why not? The answer is yes, because, and there's 2 reasons. Number 1, each individual probability is between 0 and 1. And number 2, the sum of the probabilities is 1, okay? If either of those fails to hold, then this is not considered to be a valid distribution. Let me tighten that up there a little. So that's what it takes. And if you want to write this out symbolically, which we've done in the class, you can do it in the following way. And like I said, always there's multiple ways of expressing the answers with these types of problems. If you write this out in terms of symbols, you could alternatively call it, number 1, for example, you can write it as something like this. So PXI means the probability of a specific value of x. So in other words, here we would call this x1, 2, and 3. And over here, this would be the probability of x1, x2, x3. So the I simply means for any of the x's, its probability has to be between 0 and 1. And of course, if you add those up, you'll see that they do in fact add up to 1. So the second requirement is satisfied. And you can write it like this. Now, you don't need to do both. You can write out the answer in English. You can write out these equations, but you can do both if you want. It's not absolutely necessary because they mean the same thing. Now, for part B, X is a discrete random variable because it can only assume a finite number of different values. Okay, so in other words, the mere fact that I can create a chart out of it is a hint that this is a discrete random variable, because a continuous random variable has an infinite number of possibilities, which means trying to show it in a table would require an infinite table. We can't have that. So clearly, in this case, we have a finite number of possibilities. That makes X discrete. Remember, continuous is the opposite. Continuous would mean that we have an infinite number of possibilities, which we do not have here. All right, now for the next part, we're looking at our moments again. So first, let me split up the screen so we can see what we're doing. And we need the moments. Now, because this is not one of the special cases, it is not binomial, it is not Poisson, we need to use the general formulas, which, by the way, they always work. You can always use these general formulas. You don't have to use the shortcut formulas for the binomial or the Poisson, because these will always work. Okay, so for example, C, expected value of X is obtained by multiplying each X by its own probability and then adding them up. So for example, here, what you would actually have is 100 times 0.3 plus 300 times 0.5 plus 500 times 0.2. All right, and that gives us 30 plus 150 plus 100, which is 280. Okay, so that's how that's done. Okay. Hold on 1 second. All right, very good. Now, how about D, the variance? All right, the variance is a little bit more complicated. So you have to take, for each X in your probability distribution, you're subtracting the expected value, you're squaring the difference, and then you're multiplying at the end by that probability. Okay, so it's very much like the sample and or especially the population variance, although the key difference is that here you have probabilities, which was not the case when we're dealing with samples and probabilities, samples and populations. So here you would have X1 is 100. Now we just got through proving that EX, or expected value of X, is equal to 280. So we're going to subtract 280, and then we have to square the result before multiplying by the probability that X equals 100 or 0.30. Okay, so all that information came from the first row of the table. Then we go to the second row where X is 300. Again, subtract the expected value of 280, square the difference, and now multiply by the probability of X equals X2, which is 0.5. And then for the last row, we have 500 minus 280 squared times 0.20. All right, so what you might want to do is simplify it a little. You don't have to necessarily go through every one of these individual steps. That's up to you. But you really should show some of the steps because first of all, it's easier to avoid mistakes. And secondly, it's easier for me to give you partial credits. All right. So for example, here, if I were to square negative 180, I'd get 32,400. 20 squared is 400. And 220 squared is 48,400. Oops. All right, now we can just do some multiplication. And hold on, I was inconsistent here. I need a bracket. All right, so we'll start by multiplying 32,400 times 0.3. That's 9720. Now this one you can do in your head, 200, and then 48,400 times 0.2 is 9680. And those add up to 19,600. All right. Now, last but not least, E, the standard deviation. And with the standard deviation, of course, all you're doing is taking the square root of the variance that we just got through calculating. All right, square root of 19,600. You'll probably be surprised to discover that it's an integer. This is actually exactly 140. Okay, so that's it. That's all you had to do. All right, that's cool. Now, let me just do one thing. So next, we have an M&M's Mars produces a special bag of M&M's at Easter time, which is 40% purple and 60% pink. Let's think of purple as being a success. Let's say for some reason we're only interested in finding out how many purples we get when we randomly choose 4 out of a bag. Now, already we can tell this is the binomial distribution because each M&M is either pink or purple. And furthermore, the probability of each one being pink or purple is independent of all the other M&Ms. There's no, in other words, each one has no influence on the others. It's just a bunch of M&Ms all jammed together in a bag. And we know that the bags are designed to contain 40% purple and 60% pink. So the experiment consists of picking 4 M&Ms out of the bag at random without looking. You just reach in and grab any 4 of them. And so what we're going to do is ask ourselves some probability questions based on the number of purples. So we can think of X in this case, the number of purples and X is a binomial random variable with a with n equals 4. In other words, 4 M&Ms are chosen. So there's 4 trials and pi. Now remember, we're using the Greek letter pi here to represent the probability of success. The reason they're doing that is because if they use p, there's already a lot of other variables in statistics that start with a p. So in order to avoid confusion, what they're going to do is use pi. Now, they tell us in the problem, the probability of getting a purple is 40%. Okay, so with that being said, all of these probabilities can now be calculated with the binomial distribution. That's why this matters. All of this information is just designed to tell us, yes, you can feel free to go ahead now and use the binomial distribution with n equals 4 trials and pi equals 0.40 probability of success. If not, if this were not the binomial, you would have to have a chart or a table or some other information in order to calculate these probabilities, just like we did in the previous problem. So let's start by calculating the probability of no purples. So even before we do that, let's remind ourselves what this formula looks like. So here we have to be a little careful. You've got capital X is the random variable. Lowercase x is the value of x. In other words, in this case, it's going to be 0. But we start out by writing out the formula. Now, what I'm going to do is write it out in terms of factorials. Because this is what we're actually doing to calculate our probability. Now, of course, when you're doing the actual test, you'll have access to all of your notes. If this was an in-class test, you'd have a formula sheet, and this would be on there somewhere, but you would be responsible for knowing that this is the right formula and how to use it. All right, so now we can plug in everything. We have, let's see, we know that n is 4. Quick reminder, pi is 0.4. And of course, for this first case, that lowercase x is 0. Now here I'm going to put 0.60. Just be aware that 1 minus pi is 0.60. And n minus x is 4, because it's 4 minus 0. Okay, so that's where these are coming from. So in other words, if pi is 0.4, 1 minus pi must be 0.6. And this exponent n minus x must be 4 minus 0, which is just 4. Now, here's a helpful hint here. Sometimes with these cases, you'll get some simplifications. Like here, for example, this one is going to reduce very nicely, because look what will happen. So this first term is just 1. Not only that, but the second term is also 1, because here we go, 0.40. So the 0 is just 1. And that's because in general, x to the 0 equals 1. All right, anything you raise to the 0 power is just 1. Now, by the way, let me just show you a couple of quick shortcuts with combinatorics. Anytime, now remember, this formula is the number of combinations that we can create by choosing x objects from 4. And it's often written like this. This is just a little side note. This is just to help speed things up a little. It turns out there's a couple of special cases that you might want to think about, because they'll speed up your calculations under some conditions. So here's one of them. So in other words, what this is saying is that if you have something like this, which is what we might run into. Actually, I'm sorry, I should have started here. Let's start with 0. This is what we're looking at right now. So in other words, anytime x is equal to 0, that combination, the number of combinations is just 1. All right, so no matter what the numbers are, so like here, we're being asked to calculate or, choose no objects from 4. So the number of ways of doing that is just 1. Now for this one, we have the same thing. And so if we were asked to pick 4 M&Ms out of 4, you're also going to get 1. And then here's another nice simplifying case. So like, for example, here, if I was asked to pick 1 M&M, purple M&M, there will be 4 ways of doing this. So if this is helpful, that you can go ahead and use it. I just wanted to point this out to you that there's some special cases with combinations that can make our calculations a little simpler. So when I have 4 M&Ms total, if I'm asked to pick 0 M&Ms, there's only one way of doing that. If I'm asked to calculate or pick 4 M&Ms, there's only one way to do that. If I'm asked to pick 1 M&M, there's 4 ways of doing that. Now, if you don't remember this, that's fine. You can just go through and do the calculations anyway, but I just want you to see these. And then that way, when we do the actual results, you won't be surprised. So like here, for example, it ended up being 1. Now, by the way, in this case, since we have so much cancellation going on, you've got already, that this first piece is 1. The second piece is 1. And then we're just left with 0.60 to the 4th power. And so we wind up with, let's see, 0.1296. All right, so that's your actual answer right there. Okay, so in other words, when you go back to the original equation, this is 1 and this is 1. What remains for us to calculate is the last part, 0.6 to the 4th power. So that was pretty straightforward. Now, how about B? In part B, we're being asked for the probability of 1 purple. All right, so let's do that. So let's remind ourselves that n is 4, pi is 0.4. And a quick reminder what the formula looks like. Okay, so then what's the probability that x equals 1? Now, of course, you notice this is actually, let me do this. Let me write this not as 3, but just a quick reminder. This is actually 4 minus 1, and that's why it equals 3. Okay, now here we're choosing 1 object from 4. Now, based on our special cases up here, you'll see we already know in advance that that is actually going to equal 4. Okay, because you see what's going to happen here. 4 factorial, just as an aside over here, yeah, sometimes the marker gets a little funny. Now we know that 1 factorial is just 1. So we're left with 4 times 3 times 2 times 1 over 1 times 3 times 2 times 1. So you just end up with 4. And as far as this one is concerned, anytime you raise x to the first power, you just end up with x. So what you've got here is 4 times 1, and 0.6 raised to the third power is 0.216. All right, so you multiply these out. Oh, I'm sorry, I made a completely stupid mistake here. This is not 1, it's 0.4. Watch right here. What did I do? Hold on 1 second. 0.4 raised to the first is 0.4, not 1. 0.4. Sorry about that. Because x, like I said, raised to the first power is just equal to x, not 1. All right, now we're good. 4 times 0.4 times 0.216, 0.3456. That's more like it. All right. Now, if you can get these first two, you can get any of them. I mean, they're all the same. As long as you plug in the numbers correctly and you really understand how the combinations work, there's no reason why you should ever make a mistake in these. But having said that, there's one here that's a bit of a trick question. At least one purple. All right, now let's go through that again. Now that's a special case where you can actually create a shortcut. This is, in symbols, this is equal to the probability that x is greater than or equal to 1. Now, in our case, because we only have 4 trials, what you could do, but it would take a while, is calculate all 4 of these. Yeah, there's a button on the side of this marker that if I accidentally hit it with my finger, it just starts going all over the place. It's very irritating. There doesn't seem to be any way of turning it off. Okay, this is possible, but guess what? It's not necessary. There's a shortcut. And when you see the shortcut, you'll say, wow, I like this shortcut. Watch this. In this case, when n equals 4, what can happen? There's only 5 possibilities. X has to equal either 0, 1, 2, 3, 4, or 5. Sorry, up to 4. Okay, so in other words, because there can only be 0, 1, 2, 3, or 4 successes on 4 trials, the probability of these added up is 1 because that covers every possible case. So why does that help us? All right, here's why, because all I have to do is take a little algebra and do something amazing. Okay. Watch what I'm going to do. Oh, one more thing. Keep in mind, don't forget, up here, they tell us that the probability that x equals 1 is all of these. Okay, so therefore, if you notice, all of these match up with greater than or equal to 1. So this expression can be rewritten as the probability that x equals 0 plus the probability that x is greater than or equal to 1 is 1. And therefore, oh, this is our shortcut. So when you see at least 1, what you can do is just say, oh, I get it. This is that shortcut case. All I have to do is calculate 1 minus the probability that x equals 0, which we saw earlier is 0.1296. So I just saved you a lot of work because calculating the probability that x equals 1, 2, 3, and 4 would take a while. It would give you the right answer. But why do all that work when it's not necessary? The answer is you shouldn't. Okay. Now they're asking us for the moments. If you go back to the question, expected value of variance and standard deviation. All right, very nice. So let's remind ourselves that n is 4 and pi is 0.4. All right, so n is 4. So now, because this is the binomial distribution, we can use the special formula, shortcut formulas. And look how easy that is. Now, we could have used the other approach, but that would have taken, in other words, the formulas we had earlier, where the product of all the x's times their own probabilities, that would require us to calculate all the individual probabilities and then use a more complicated formula. So we don't want to do that. Instead, look how simple this is. And then, of course, the standard deviations, very simply, square root of the variance. And that's approximately equal to 0.98. Wow. And that's it. And so pretty much, so all follow along the same pattern. You'll be asked to calculate a few probabilities and then calculate the moments. After first, of course, recognizing that this is the binomial distribution. All right, now the next one you can see is another binomial problem. Now here we're taking a bit of a liberty here. We're going to assume that everybody is either left-handed or right-handed. Now we know perfectly well that some people are ambidextrous, but most of those people are actually lefties who are also very good at their right hand, or at least that's been my experience. So let's just assume, to keep it simple, that everybody is either left-handed or else they're right-handed. Or if you prefer to think about it another way, you can think of everyone as either being left-handed or not left-handed. You can always break it down that way too. But let's just say, to keep it as simple as possible, 10% are lefties, 90% are righties. Now, by the way, it doesn't explicitly say the words left-handed means a success, but you know how you can tell, because all the questions have something to do with lefties. Okay, so in other words, the mere fact that it's asking about the probabilities of lefties indicates that you can assume that being a lefty or left-handed is a success. Okay, and so for that reason, we can say that X is the number of left-handers, and because there's 9 people in the group, each one of them could be considered a trial where they're either left-handed or they are not. And then it tells us here that statistics show that about 10% of the population is left-handed. So pi is 0.10. And now we can go on with our normal procedure. So once again, I'll remind you what this formula looks like. Okay, and also we have n and pi right here. So therefore, for the first one, the probability that x equals 0, we have 9 factorial over 0 factorial. Here we have 0.10 to the x power . That exponent is actually 9 minus 0. So, and here we have another scenario like we had before. Remember, this is one of those special cases to choose 0 objects from 9 can only happen one way. Okay, so even though up here it was 4, you can see that when you calculate this formula, those 9 factorials will actually cancel each other out. 0 factorial is just 1. And 0.1 to the 0 power is, of course, just 1. So really, all you have to calculate is 0.9 to the 9th power to come up with your answer, which is about 3874. Okay. So then the next one is the probability of getting 2 lefties in the class. All right, so 9 factorial over 2 factorial, 9 minus 2 factorial. Actually, let me clean that up a little. All right, let's see what we can do with this one. All right, now this one, we actually have to do the calculations. For these combinations, there's no formula for this one. We just have to calculate it. Now, if you throw this into your calculator, though, you'll see that, whoops, hold on. $36, that it reduces to 36. Okay, now let's do a little side note here. There's a lot of canceling going on here. Okay, so in other words, all of this and all of this drops out. So you're left with 9 times 8 over 2, 72 halves, which is 36. Now, 0.1 squared is 0.01. And then finally, 0.9 to the 7th is 0.4783. And by the way, with these, unless the number is really, really small, you can feel free to round it to 4 places. That should be good enough. So this is about 0.1722. All right, now part C was, let's go back and grab it. At least one, there it is again, our old friend, at least one, okay. So we'll use the shortcut, of course. And remember, we already calculated the probability that x equals 0. It was 3874. To end up with 0.6126. All right. Well, that was nice and easy. And then we're just going to do the moments. We always want to do the moments. All right. So just remember that n this time is 9. I is 0.1. So we expect in a class of 9, there's 0.9 lefties. Well, I know there can't be 0.9 lefties, but on average, if we keep having classes of size 9, actually, let me do one thing here. All right. Just a reminder what the actual formula is. Okay. And now F the standard deviation is very simply the square root of the variance, and then we end up, interestingly enough, right back at 0.9, just by coincidence. All right, so those are our moments. All right, now the next one is a little different. On average, 3 customers enter a bank every hour. All right, so already we know that this is different because there's time involved. Once you see that, that tells you right away that this is the Poisson distribution. And furthermore, we know that that parameter lambda equals 3. How do you know that? Because on average, 3 customers enter the bank every hour. So now let's remind ourselves the probability formula for the Poisson distribution. Now, of course, we don't know what factorial means. Lambda is given to you. E, remember, is a constant. It's approximately equal to 2.71828. It is on your calculator. And so you should have no trouble raising it to different powers. So for A, the probability that no customers enter the bank in the next hour. So remember, lambda is 3. That won't change throughout this problem. Now, by the way, here again, we have a lot of cancellation because 3 to the 0 power is just 1, and 0 factorial is 1. So all we need is e to the minus 3 power. And if you go to your calculator, you'll see that that's approximately 0.0498, let's say. All right, and the rest are done in exactly the same way. B, for example, is the probability that x equals 1. So now remember the formula, just slide this down a little bit, tells us we have e to the, now this is still e to the minus 3. 3 is lambda. 3 is now raised to the first power though. And in the denominator, we have 1 factorial because that is x factorial. So here, there's less cancellation. We actually have e to the minus 3 times 3 over 1. So you're basically, or you can rewrite that as e to the minus 3 times 3. And that means it's 3 times what we had in the previous question. Oh, whoops, I put an extra 0 in there. Hold on. Point 1494. All right. Now, the next one's interesting because it's asking for the probability of 2 or 3 customers. So this is an important detail. 2 or 3 customers. So the probability in a case like this, that there will be 2 or 3 customers during the coming hour can be calculated as, so what you're basically doing is calculating each individual probability and adding them up. Okay, so this is true for any case where you have the word or there. Now, we're not going to encounter the word and in these cases because it's not possible for there to be both 2 and 3 customers in the coming hour. But if you have an or, that means it's either one or the other. So you have to calculate each one separately and then add them up. All right, so again, let's quickly remind ourselves that lambda equals 3. And that the formula is okay. So for 2, all right, so here we can simplify it a little bit. 3 squared is 9. And so now remember earlier, we figured out that e to the minus 3 is 0.0498. And so this time we have 0.2241. Now, for x equals 3, e to the minus third. Now, this time, lambda is raised to the third power, and then we have 3 factorial. Well, guess what? 27 over 6 is 9/2. So it's the same number. How do you like that? It does happen with Poisson sometimes. You get 2 values of x that have the same probability. It's not that unusual. So when we're done, look how easy this becomes. And there's your answer. And that's it, you're done. All right, so in other words, anytime you have that or in there, just add up the individual probabilities and you're all set. It's not just because it's Poisson, for anything, binomial, normal, you name it. The word or indicates you're taking different probabilities and adding them up. Now, as usual, we need the moments, except remember for Poisson, the moments are a little bit different. The expected value, for example, is lambda. The variance is just lambda. And the standard deviation would therefore be the square root of lambda. Which is approximately 1.73. All right. Beautiful. All right. So let's see what's coming next. Now the next one is not Poisson. It is standard. Now you see how it says the word standard normal, which means the case where the mean is 0 and the standard deviation is 1. In other words, this is the case that we see on our tables. So I'm going to go open up the tables because I forgot all about it. Hold on one second. So we'll need both normal tables, 1, which has all the positive values, and 2, which is all the negative values, to do these probabilities. All right. Now, since we just got through doing this stuff, this should be pretty fresh in your memory. These others you might have started to forget a little bit, although in such a short class, I mean, really, the oldest material we've done is slightly over 2 weeks old. So that's where this kind of, crammed in semester can be very helpful. It's hard to forget things you did 2 weeks ago. If this was a full-length semester, we might be talking about topics we covered 8 weeks ago. And that makes a big difference, doesn't it? Anyway, so here we go. So here we have a set of probabilities for the standard normal distribution. And that just basically means we can find things in the table, of course, if they're in the correct format. So like this one should be rewritten as 1 minus the probability that z is less than or equal to 0, because the table only shows, as we know, greater than less than or equal to probabilities. So 0 on the positive table means that we're looking, now the 0 is actually in the extreme upper left-hand corner. And so you can think of 0 as 0.00. This is coming in the first column, and this part is coming in the top row. And where they overlap, you see that's 0.5. But remember too, that by definition, since 0 is the mean, the probability of being above the mean is 1/2. The probability of being below the mean is also 1/2. So you in a case like this, you don't really even need the table if you remember that. And you can just write it that this is true by definition, or you can just do it the traditional way by grabbing it from the table and you're done. Now, less than or equal to negative 1.88, that one we can just go directly to the negative table. All right, so let's go to the negative table. Negative 188. Hold on. So you need the negative 1.8 combined with 0.08. Actually, I shouldn't have written it like that. Now, by the way, this obviously should be a negative. I don't know why they leave these positive, but negative 1.8 with 0.08, where they intersect is here at 0.0301. There you go. It should be negatives in the top there too, but they're not. Whoops. Here we go. Now for this one, greater than or equal to negative 1.36, right away, we know that this can be rewritten as 1 minus the probability that z is less or equal to negative 1.36. And again, we just go right back to the negative table. Okay, so we need the combination of negative 1.3 and 0.06. .0869. All right, now remember though, we have to subtract that. So the 0.0869 is not the final answer. It's actually 0.9131. All right, and then finally we have D. We have D, negative 187, negative 0.53. Now with these in between probabilities, we rewrite it as the probability that z is less or equal to negative 0.53 minus the probability that z is less or equal to negative 1.87. All right, so negative 0.53, we can find it on our table. Okay, so this one's, well, it's way down here. Hold on. All right, so I know I wanted to cram it all in there. Negative 0.53 is 0.2981. And negative 1.87 is 0.0307. All right. 0.2981, 0.0307. The difference is 0.2674. And that's our final answer. All right. So we covered all the possibilities here. We've got a greater than or equal to, less than, and in between. All right. Now down here, we can see it already mentions the word normal. Right here. But if you notice, this is not the standard normal distribution. How do you know? Because the mean is 12% and the standard deviation is 30%. So we'll use the letter X to represent this these rates of return to this global growth fund. So we said that X is normal, the mean, and because it's a percent, we'll rewrite it as a decimal. So what that means then is that we're going to calculate some normal probabilities here, but we'll need to use this conversion formula in order to access the tables. All right, so we didn't need to do that before because it was already the standard normal distribution. All right, so we'll start with less than 12%. All right, so we'll subtract the mean of 12 and we'll divide by the standard deviation of 30. All right, so actually, let me add this one thing here. In this case, every time we're subtracting 0.12 and we're dividing by 0.30. Well, guess what? It's 0. And we've already seen, we don't even have to look it up again. It's 0.5 because half the distribution is below the mean. Now here, if you notice this diagram, the mean is 0.12, which implies that the probability of being below 12 has to be a half. In other words, the probability that Z is less than 0 is the same thing as the probability that X is less than or equal to 1/2. Okay, so in other words, remember, those are it's like the difference between Celsius and Fahrenheit. It's the same thing, except with different units. All right, so either way, it's a half. All right, the next one, although you can't see it there, is more than 27%. All right, let me move that down here. Quick reminder, The mean in these cases is 12%. All right. More than 27. All right, so of course, we will subtract so when you subtract, this actually turns out to be okay, z greater than or equal to 0.5. All right, so we're looking at more than half a standard deviation above the mean. And as far as the table is concerned, we can rewrite that as the probability that z is less than or equal to a half. So let's go look that up in the table, 0.5. The positive table, that is. And here we go. So think of 0.5 as 0.5 plus 0.00. And so it's here 0.6915. That's the probability of being less than or equal to and that's the final answer. Okay, now for part C, the probability is less than -3%. And of course, we're going to rewrite that as we subtract the 12, divide by 0.30. Oh my God, somebody put something in the chat room and I never saw it. Sorry about that. Let me take a look at this. Do you always subtract? No. Oh, yes. Sorry. Yes, you do in these cases. You subtract the mean and you divide by the standard deviation. Okay. I hope that's the question you're referring to. That could have been sitting there for 20 minutes and I never would have seen it. So sorry, Cecilia. I didn't see your question. Oh, no. It's just, okay, good. I just want to make sure you didn't think I was ignoring you. You know, the problem is it used to be the way they set this thing up is that when somebody put up something in the chat room, there would be a little light that would flash and they somehow stopped doing that. And so it's easy for me to overlook chats. So if it looks like I'm not seeing it, you can just throw it up there again and hopefully I'll see it. But yes, it's always the same format. You always subtract the mean of 12% in this case and divide by the standard deviation of 0.30. So that what you end up with is a standard normal random variable instead of just normal. Okay, so it's like I said, I think of it as like converting Fahrenheit into Celsius because it really is the same principle. Now this time though, we end up with less than or equal to -0.5. And so when we look that up in our negative table, let's see, where's my negative? Here it is. Oh, we had, no, we don't have this one. We have something similar. The -0.5 is all the way down here. Here's the 0.00, 0.3085. All right, so that's the final answer. By the way, if you notice, It's the same as this one, because look at what we're being asked to do. Greater than 0.5, less than negative 0.5. Let me just show you a little picture to show you why these turned out to be the same number. Because of the symmetry of the distribution, this section, this is part C. Part D, as part B rather, was the probability that Z is greater than or equal to 0.5. So they have to be the same number. Okay. So in other words, what I'm saying is you should not be surprised to notice that these are exactly the same answers. They should be the same. Beautiful. Now for D, we're looking for the probability. This is an in-between problem. Between negative 0.18 and 0.42. And so once again, we're going to subtract from each one of these 0.12. All right, so we have negative 0.30. So what we wind up with is the probability that Z is between negative and positive 0.1. Now, by the way, when we first introduced this topic, we've already actually done this one. This is one of those special cases. But we're going to do it the normal way anyway, but I just want to remind you. Yeah, when we first introduced this topic, we did a few diagrams like this one. Being within one standard deviation of the mean should give us a probability of approximately 0.6826. But we're going to prove it now by recalling that whenever you have an in-between case, what you're actually doing is subtracting the smaller one from the larger one. Okay, and then these, of course, we can look them up directly in the tables. For example, 1, let's go to the positive table and find it. So 1 could be rewritten as so we have 0.8413 minus 1 then from the negative table. All right, minus 1 combined with 0.00 is 0.1587. And so if you subtract one from the other, guess what you end up with? There you go. And that's why this is happening. So roughly 2/3 of the distribution is within one standard deviation of the mean. So, you can think of this in real world applications. If you think in terms of, let's say, heights, the vast majority of the people are within one standard deviation of the mean. I mean, sure, you get some very tall people and some very short people, but the overwhelming majority are fairly close to each other as far as height is concerned, roughly within one standard deviation of the mean. You ever notice that? You do see most people, if you really look, their heights are relatively similar to each other. All right, anyway. And then we have one more in-betweener, I guess we could call it. Part E asks us to do this. So we subtract. And we end up in this case and when we actually do the calculations, we'll see that this time we're looking at the probability that Z is between -0.5 and +0.5. All right, and so once again, since this is an in-between problem, we can subtract one from the other. And then we can easily look these up in the two tables. 0.5 on the positive table is right here. 0.6915. And -0.5 on the negative table is right here. 0.3085. And so we should end up with um, .3830. All right, so that wasn't too bad. So there's only one more question. This involves the normal approximation to the binomial. Now, it doesn't actually say that, but we'll see why in a minute. So first, since it's so late, let's have our break. And when we get back, we'll wrap up this last problem, and then we can dive into chapter 9. Yes, we're getting towards the end already, because there's only 10 chapters. So we'll do at least some of 9 today. And I'll post, when we're done, I'll post the actual midterm, and I'll announce the due date, and then we can take it from there. All right, so go ahead and have something to eat or drink, and then when we come back, we'll wrap this up, and then we'll start 9. All right. All right. So one more problem here. And now this time we've got a coin being flipped 1,000 times, and X is defined as the number of heads. Now, clearly this is a binomial problem, but if you notice, we have a huge number of trials. And so calculating probabilities here will be very difficult if we use the binomial distribution. Like look at D, between 480 and 520 heads. To do that directly with the binomial distribution, you're looking at 41 probabilities, which you have to calculate and then add them up. So that's why we're going to use the normal approximation to the binomial random distribution, even though it doesn't say to do that. The hint that you should use this approach is the fact that there's just so many trials. That usually means go ahead, use the normal approximation. So the first thing we want to do is write down some of the key details. For example, we know that there are 1,000 trials because the coin is being flipped 1,000 times. So X, the number of heads. X is a binomial random variable with 1,000 trials, and pi, probability of success, is of course a half, because that's the probability of getting ahead when we flip the coin once. All right. So now they're asking us for the moments first, because we're going to use them in our calculations. All right. Normally that comes last, but in this case, it's much more useful to calculate these first. So for A, the expected value, of course, is n times pi, 1,000 times a half, or 500. All right. Then what about B, the variance? So you might recall from earlier, the formula for the variance of a binomial random variable is n times pi times 1 minus pi. And that's 250. All right. And then finally, the standard deviation. And the square root of 250 is approximately 15.81. Now, for part D, they're asking us to calculate the probability that there will be somewhere between 480 and 520 heads. That's a lot of calculations. So what we're going to do is the first step is to apply the continuity correction which means add 0.5 to the upper limit, subtract a half from the lower limit. So what we're actually going to calculate is the probability that X is between 479.5 and 520.5. Now we can convert X, what X is being treated is a normal random variable. It is now converted to a standard normal random variable like we've been doing all along, except now we're actually doing this. Because now remember, the normal formula is this. The reason why we're changing it is because the mean of the binomial random variable is n pi, and the standard deviation is the square root of n pi 1 minus pi. So we're going to have x minus 500 from up here. The expected value is 500 and the standard deviation is 1581. So for all the remaining cases, we'll be subtracting 500 and dividing by 15.81. All right, so now we can go and apply this to our range here. Now this is the one that's already had the continuity correction applied to it. Okay. First, let me save this. You always should save everything you're doing as often as possible, because you never know what might happen, especially if you're worried that you may not have quite enough memory here. Yeah, we're getting close. Oh God, I can tell it's already too much. Okay, this is not good. So here's what I'm going to have to do. Unfortunately, I already called this part 3. Oh, for God's sake. All right, what I'm going to do is see if I can save this as part 4 as well. Hold on 1 second. Yeah, I knew it. I was pushing my luck. What I'm going to do is split off some of this into a new document. Actually, I have a better idea. No, I think it's too much. It's just so irritating. Well, you know what? Actually, so we started here. Unbelievable. See, when it does this, that means it's out of memory. It's being a pain in the butt. All right, let's try this. No. See, the thing is, it won't even let me save parts of it. It's absolutely useless. What a piece of garbage. All right, let me see if I can save it with a new name on the desktop. Or just save it the way it is. No. All right, you know what? Instead of messing around with it now, I'll figure it out when we're done. I may have to redo some of this. I've seen this before and it's not pretty. I'll just carry on and then I'll figure out how to save it later on. I can't be holding this up here. All right, so what's gonna happen is that now I'm gonna subtract, like I said, 500 and divide by 15.81. And so here, we're going to have so this one is approximately equal to, let's see, this is 479.5 minus 500 divided by 15.81 minus, this is about negative 1.30. And this is 1.30. So we know what to do now. It's we subtract the differences. Now we look these up in the tables. Or let's go get positive 1.3 first. Okay, 1.3, 1.0 combined with, sorry, oh no, sorry, that's the wrong one. It's 1.3 combined with 00. Okay, so 1.3. All right. 0.9032. All right, so we'll put that in here. And then on the negative table, negative 1.3 combined with 0.00. So here's the negative 1.3. This is the 0.00 column, 0.0968. And the difference between the two is 0.8064. Okay, now for the next part, it's asking for more than 525 heads. Now, this is actually the lower limit. So what we usually do in these cases is you can first rewrite this. And what we're going to do is just adjust the lower limit. And so with the continuity correction, and then like before, we're going to subtract 500 divide by 1581. So this one works out to be about 1.55. Actually, now that I look at it, I probably shouldn't have rewritten it like this because, I mean, I wanted us to see that that's the lower limit, but I think it would be easier. Let's do this. Because then it's clear that we have to subtract this from 1. In other words, z is greater than or equal to 1.55. We're going to subtract that from the probability that z is less than or equal to 1.55 because we need to get that from the table. And so that would be .9394. And the actual answer will be 0.0606. All right, and then there's one more piece. And that is part F, less than 485 heads. So this one's pretty straightforward. The continuity correction tells us to simply add a half to the upper limit. And then we're going to subtract 500. And divide by 1581. All right, so this is equal to negative 0.92. And of course, that's right on the table, so we can just go look it up right now. Negative 0.92. So you have the combination negative 0.9 and 0.02, 0.1788. And that's it, we're done. All right, so I'll figure out how to save this damn thing, and then I'll post it as part 3, or if I need to, split it up into 2 parts. But so these are the answers. We're done. So now we can go ahead and go back to chapter 9 for the first time. And 9 does include the normal distribution, but it also introduces the a brand new probability distribution. And so those 2 distributions will be used in this chapter as well as chapter 10. Okay, so we started to briefly look at this yesterday. Confidence intervals, the idea behind a confidence interval is that you want to understand the properties of a population parameter like the mean, but instead of providing a single number, you provide a range of values. For example, let's take a look at this one. Suppose we're interested in analyzing the gas prices in the US. Now, this is a little outdated. I should add $1 to both the lower and the upper limit. But let's say that 95% confidence, what we're saying here in this example is that the average in our sample is $3.19. But what we're finding out is that we know that there's uncertainty associated with this mean. This may not be the population mean. And in fact, we're willing to acknowledge that the population mean could be up to 20 cents lower than that and up to 20 cents higher than that. So in other words, that 20 cents is what we're going to call our margin of error. How much uncertainty is there associated with this X bar? So that provides us with a range. So what we're basically saying is two things. Number one, the sample mean is 319, which we believe represents the population mean, but we're also 95% sure that the actual population mean is somewhere between 299 and 339. Because we know that that X bar isn't necessarily a perfect reflection of the population mean. It's possible that it's off by up to 20 cents in either direction. And of course, there's still a chance, a very small chance, that the actual mean is even further away. It could still be less than 299 or higher than 339, but it's highly unlikely. We're quite confident that the true value is somewhere between 299 and 339. Now, the big question here is, where did we come up with the margin of error? We know how to calculate a sample mean. The question remains, where did that margin of error come from? That's what we're about to calculate. And once we've got a margin of error, we can calculate a confidence interval for any situation we might need. All right, and so since this is an interval, that 299, we'll call it the lower limit of the interval, and that 339 will be considered the upper limit of that same interval. X bar will be the center of that limit, of that interval rather. Okay, sorry, so let's jump ahead a little bit here. In statistics, we use what are called estimators. This is just terminology. You don't really need to memorize this. I won't ask about it on the test, but an estimator is a formula that is used to calculate or estimate a population parameter. In other words, X bar itself, the formula that we use for X bar in statistics, this is formally known as a point estimator. Now, the word point simply means it provides us with a single value. The word estimator means it's a formula that is being used to let us calculate or estimate the value of the population mean. Now, once we have our actual number, suppose that we calculate X bar as, let's say, 10. Well, then we would say 10 is a point estimate of mu. And here I should have put that in here as well, of mu. So in other words, what they're telling us is that the word point means a single value, and the word estimator refers to the formula for X bar here, whereas estimate is the actual value of X bar. Again, I won't ask about this on the test, but it's good to know what these terms actually mean. Now, why are we introducing this now? Because we want to compare this with what's called an interval estimator and an interval estimate. So in other words, a point estimator or a point estimate is a single number or formula. An interval estimator is a range of values. Okay, so the confidence intervals that we will be constructing is a type of interval estimator. It's not the only one, but it gives us a range of values. In other words, it provides a range of values instead of a single value. And that's where the word interval comes in. Interval as opposed to point. Point means single value, interval means a range of values. Okay, so that's what we're actually doing here. Now, what we're going to do is see that assuming, or for any confidence interval, the basic layout is this. We have some point estimate. For example, it could be X bar. And then we have the so-called margin of error, which we've really already discussed. This reflects the uncertainty associated with using X bar to estimate mu. And why is this happening? Because we know that every sample is different. If we keep choosing samples, every X bar from each of these samples could be different. And in some cases, they can be very different. In some cases, they'll be very close. So the margin of error indicates how close the X bars are likely to be each other if we continuously sample from a population. So that's our basic structure. Now, there's two basic cases that we'll see in this section. And the decision as to which one to use depends on this population standard deviation. We're going to assume there's only really two possibilities. Either we know what it is or we don't. So we're going to start with a case where the population standard deviation is known because that enables us to use our old friend, the normal distribution. So when the standard deviation of the population is known, then, and you notice the Z here, this is the standard normal random variable. And if you notice everything to the right of that plus and minus sign, this is all the so-called margin of error. Now, plus, you know what plus and minus means. Like this means that you're going to take X bar minus all of this. And you're also going to do the same thing with plus, and that way you'll have a lower and an upper limit. All right, so this is my lower limit. This is my upper limit. They're obtained by taking X bar and in the first case, subtracting the margin of error, and in the second case, adding it. So you come up with two numbers, the lower limit and the upper limit. Oops, sorry. Now, and then it does say in the next slide that this is our margin of error, and that reflects the uncertainty of X bar. Now, the one piece in here, if you notice, we've got this little subscript. We haven't seen this before. This is an important detail. First of all, this is the Greek letter alpha. And the alpha reflects the level of confidence in our confidence interval. Now, I just want to mention in passing here, typically confidence intervals take one of three, there'll be one of three forms. All right. Most of the time, confidence intervals are constructed with the following levels of confidence, as they're called. So most of the time, we'll either use 90%, 95%, or 99%. It's not impossible to do any of the others. It's just that these are the ones that you see the most often. And usually in practice, the most popular one is 95. You see it everywhere. It just makes sense to people. 95%. I'm 95% sure that this is how long it takes to get to, let's say, I'm driving to Philadelphia and I want to know roughly how long it should take. And somebody says, well, it should take about 3 hours, give or take 20 minutes. It's the give or take part that represents how much uncertainty there is associated with this commute. If there's a lot of traffic along the way, then the uncertainty grows proportionately. If the weather is bad, then the uncertainty also increases. So the confidence level that we're seeing here reflects how much uncertainty there is associated with our estimates. And so we normally go with 90, 95, or 99. So we'll be prepared for all three cases. Now, by the way, one more thing, this is more terminology. We won't need this until the next chapter, but alpha is sometimes referred to as the level of significance. And Z, when it has that little alpha there, we often call it a critical value or a Z-score. So more terminology, like we need more. And then this piece by itself is sometimes called the standard error of X bar. Okay, now remember, we saw this in chapter 8. This is the small sample case. All right, but here, that's the only case we'll be using. All right, so that we've seen before. This is known as the standard error of X bar. This is something we haven't done yet, the so-called critical value. And then alpha, which we know reflects the uncertainty in this process, is often called the level of significance. Okay, so how does this alpha work? Let's say that alpha is 0.05, just to make this concrete here. Then 1 minus alpha, or 0.95, is known as the confidence coefficient. And if we multiply it by 100, then this 95% is known as a confidence level. Most of the time, we'll think in terms of the confidence level. So the alpha tells us what that confidence level is. All right, but like I said, we'll typically only need 90, 95, and 99. The others, well, you could use them, but we typically don't. Like, for example, who cares about the 87th level of confidence? It just isn't done. All right, now, let's say that you've decided that you want to create a 99% confidence level. Let me just show you with a graph what this is actually all about. You're going to the standard normal distribution. And you're saying, oh, I know what I want to do. I want to find two values where 99% of the distribution is in between. If that's the case, then this area is 0.5%, as is this one. So there are two Z-scores, which form the boundaries between the middle 99% and the outside 0.5% in each tail. So this number, Z alpha over 2, is a Z-score. such that the probability of going past that point is 0.5%. Now that's going to be a large number because that's, 0.5% is a tiny value. So we can find this from the tables, but we're going to do it in a very different way than what we're used to seeing. And by the way, we have to be able to do the same thing for 95% and 90. So since this is a fairly complicated process, and since it's almost 12:30 on our last day of the week, our last class of the week, I think it might be better to start this fresh on Monday rather than try to carry on with it now, because what we have to do now is fairly involved. And I'd like to start it at the very beginning of the class on Monday rather than try to cram it in now. So we'll stop right here. And so what I'm going to do is attempt to get that document fixed so that I can post the, that part 3 set of solutions. And then 9 and 10, by the way, have already been posted as well as their problem sets. So we only have basically one more week to go, actually 1 week and one more session the following Monday. So what we need to do is finish up chapters 9 and 10 and then do the sample final, which is based on chapters 8, 9, and 10 only, not comprehensive, just 8, 9, and 10. And in the meantime, we're going to have all the problem sets. Now, let me just do one thing. Let me look at the announcements. I don't remember what I said about the chapter 6 and 7 problem sets, which we certainly want to get out of the way now because we're well familiar with those chapters. And in fact, we have to worry about chapter 8 problem set now because we are done with chapter 8. Let's see, what did I say here? Chapter 5 was due on Tuesday, yesterday, I mean. So, well, I'll tell you what. It says here, you know what? I'll tell you what. You can hand them both in by next Monday. That's fine. All right. If you've already handed in 6, that's great. I'm glad that you're so efficient. But you know what? If you haven't done 6 yet, you can hand it in with 7 next Monday. And then, unfortunately, I guess what we're going to have to do here is have chapter 8 be due that Wednesday. But remember, we do have until the following Monday. Next Wednesday is the 12th. All right, that sounds good. And also, I'll put another announcement here, update on chapter 6 problem set. So in other words, just to summarize this. And by the way, when the dates, like for example, when it says the 10th, it means midnight on that date. All right. So in other words, when it says Monday, it means Monday at midnight. So you really actually have the whole day if you need it. Okay. So that way like I said, I do not want to have a situation where all of a sudden you have to hand in 4 or 5 assignments at the last minute. I'm trying to spread them out as much as humanly possible, given that we only have 4 weeks. So this way, I think we'll be in pretty good shape. And so, as always, we're coming right down to the wire. We've got only 4 more sessions to do 2 fairly complicated chapters, but I think we'll get it done. And of course, the sample final. So I think we can just about finish it all. And then the day after we're done, I think the next day, school starts up again. The spring semester, you'll probably have to go back to school on that Tuesday. And so this is really cutting it close, but at least everybody will be done and you'll have all this wonderful knowledge that you didn't have before, which you can use in your other classes. So, all right, I guess we can stop it here. So just try to remember those problem sets. And as soon as I can, I'll get those solutions posted on Moodle. Okay. All right. So if there's no last minute questions, I'll see you all on Monday.
Hi.
Oh,
I
yeah.
have a
Go ahead.
question, but it's
Oh,
like more of a personal
thank-
question. So
hold
I'm
on
happy.
a second. Oh, okay. No, they're just saying thank you. If it's a personal question, you might want to wait until everybody else is logged off.
Yeah, yeah.
Okay. All right. Let's give that a minute. Um, Now, by the way, I don't know if you're aware of it, but you can send me a message in the chat room that nobody else can see. If if we have to sit here for a while. It's like nobody wants to go home. Well, we can start, but yeah, we can stop the recording right now. But I mean, okay, hold on. I think we have to wait for one more. I think two includes me. Yes. All right, go ahead.
Yeah, I was just wondering really quickly, because I know that you sent me a confirmation email saying that you'd received my chapter 5 problem set.
Yes, I have.
So
Yeah.
I just wanted to make sure that you'd received my chapter 3 problem set as well.
Oh, did I forget to tell you that? Oh, I apologize. I did. I remember I was looking at them last night. I was getting them organized, and yeah, I have it. Don't worry.
Okay.
I forgot. I apologize
Oh,
for
no,
that.
no, 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 no worries at all. I just wanted to check.
Yeah,
And then I just want to confirm this. 'Cause I think you did mention this, but for decimals, it's fine to stop at 4 places and then
yeah,
round.
yeah. That's fine. I mean,
Okay.
unless it's now, if you have a number that's like 0.00005 or something like that, then of course you don't want to round it too much. But for anything else, 4 is plenty.
Okay. Okay. Great.
Yeah.
Thank you so much.
Yeah, I mean, I'm not looking for, like this is not like we're not dealing with neutrons or electrons here where the weights are infinitesimally small.
Yeah.
If the probability is 0.3219 and you get 3218, it's not a problem. It's understood that there's likely to be some rounding anyway. So 4 places is more than enough.
Yeah. And then also I had a quick question on the
Uh-huh.
sample term.
Yeah,
So on the 14th question,
yeah,
so you're looking at, sort of like a binomial
right,
question, and then we're converting it to standard normal. And you
right.
took one step that I wasn't sure about,
Oh,
and that's where you like added 0.5 and
yeah,
subtracted.
you know what? The only reason we do that is because it's been found from experience to improve the approximation. That's the only reason it's being done. There's no theoretical reason for doing that.
Okay.
But statisticians have discovered from experience that it seems to improve the approximation. So that's the only reason we do it.
And then, if a question explicitly states that it's standard normal,
Right.
then you don't have to take those steps, and that's pretty clear. But if it's looking like it's binomial or like Poisson, you would have to convert it to standard normal, or would you not do that for Poisson at all?
No, Poisson doesn't need to be converted. It's
Okay.
only when you have normal, which is like any normal random variable, which is not standard normal, has to
Mhm.
be converted.
Yes.
Okay, to use the tables.
Mhm.
The other case you might run into is the normal approximation of the binomial, and then you do want it to be turned into a standard normal because otherwise you can't use the tables.
Okay, yes. That makes sense to me.
Okay.
Okay. Thank you so much.
Okay, you're welcome.
All right, have a good day.
All right. Okay, bye.